Welcome to the first talk of the spring session of the New York Combinatorics Seminar. Our speaker today is Professor Vinayak Joshi from Savitribai Phule Pune University, and he will talk about chordal and perfect zero-divisor graphs of posets and applications to graphs associated with algebraic structures. Thank you. The floor is yours.
Thank you. First, I would like to thank Professor Sandra and the organizing team for giving me the opportunity to discuss the work on chordal perfect zero-divisor graphs. This is a joint work with my student, Nilesh Khandekar. Let me give you a brief idea. As all of we know that in 1878, Arthur Cayley associated a graph with a group, now known as the Cayley graph of a group. This might be the first attempt to study the algebraic structures using graph theory. And since then, many researchers associated graph with algebraic structures and order structures. From last 3 decades, there has been ever-growing interest in the study of zero-divisor graphs of algebraic structures as well as order structures. Istvan Bek in 1988 introduced the concept of zero-divisor graphs of a commutative ring with unity, where he considered the vertex set to be the set of all elements of the ring R, and 2 vertices X and Y are adjacent if their product is 0. One can see that if units are there, units are adjacent to 0 only. So these, and they are not adjacent to each other. So that will form an independent set. So this will not give much information. So afterwards, Anderson and Livingston removed these units, and instead of considering all vertices of all elements of ring to be the vertices, they consider only non-zero zero-divisors. That was the change in the vertex set, but adjacency remained same. And he was mainly interested in coloring of graph, which is a central problem in graph theory. So in this talk, my plan is to discuss the perfect zero-divisor graphs and chordal zero-divisor graphs. And as I was discussing with the Professor Sandra, that I'm working on some sort of unification, because nowadays many graphs are associated with many algebraic structures. Few of them I quoted here. One is the zero-divisor graphs of rings. Another one is the comaximal ideal graphs of rings, annihilating ideal graphs of rings, intersection graphs of ideals of rings, intersection graphs of subgroups of groups. These are the various graphs associated with algebraic structures. And what we observed, there is a unifying pattern in the study of these graphs. So many properties of these graphs are studied parallelly. That means perfectness for comaximal graphs, perfectness for annihilating ideal graphs, likewise. So properties are repeated for each of the graphs. So why not unify them? So that is what my idea is. So mainly I will focus on 2 results only, and then I will move to the application part. And there we will see how these graphs are related with the zero-divisor graphs of ordered sets. So this is what the plan is. So let me give you a formal definition. Let R be a commutative ring with unity. Gamma R be a simple undirected graph with the vertex set where the vertex set is the non-zero zero-divisors, and 2 distinct vertices X and Y are adjacent if their product is 0. And let me give you a brief example here. I have shown the zero-divisor graph of Z12, which is weakly perfect. By weakly perfect, we mean clique number is same as chromatic number. You can see that 2 and 6 are adjacent because their product is 0. Likewise, the adjacency you can see here, but 2 and 10, they are not adjacent, and we are considering only non-zero zero-divisor graphs. So you can see that 2 colors are required, and clique number is also 2, so the graph is weakly perfect. In fact, Bek, while defining the zero-divisor graph, the first result which he proved was for reduced string. If the clique number is finite, then the graph is weakly perfect. And in fact, it has to do with the cardinality of min-r. meaning thereby you need the number of colors to color this graph is nothing but the cardinality of min R. That is the cardinality of minimal prime ideals of that ring R. So on one part you have a chromatic number, click number, completely algebraic graph theoretic aspect. On second part you have algebraic aspect. And if you look at the previous example, we have Z12 which is not reduced, and in particular he proved that the zero-divisor graph of Zn is also weakly perfect. So in general, you can see that in the case of Zn where n may not be a square free, it will be a reduced ring. But in case of reduced ring, we do have weakly perfectness. So natural question arised here was whether the graphs are weakly perfect. But later, Anderson and Nasir gave a counter example to this conjecture with a local ring of 32 elements. So this was the little bit of history of zero-divisor graphs. Let me give you the main idea. As I told you, I'm going to do the unification of all these graphs with zero-divisor graphs of ordered sets. So let me give you some terminology from ordered set. So let P be a poset and A be a subset of P. Then you define AL to be a set of all those elements B in P such that B is less equal A for every A in A. And an element X is said to be zero divisor if there is non-zero Y such that XYL is zero. Those elements which are not in zero divisors, they are called as dense elements. And a semi-ideal is a down-directed set of a poset P. On similar lines of prime ideals, we have a prime semi-ideals in posets. A proper semi-ideal I of P is said to be prime semi-ideal. If XY is in I, then X is there or Y is there. Now, with this brief terminology, let us give a formal definition of zero-divisor graph of a poset P. And onwards, we will denote it by GP. So the vertex set is again set of non-zero zero divisors. And instead of XY is 0, we have the lower cone of X and Y is 0. So that is the change. So if the lower cone of A and B is 0, then A and B are adjacent in the graph. So this is what we have the zero divisor graph. Let me give you a simple example so that idea will be much more clear. So I'm considering left-hand side is my lattice 2⁻3, that is a power set of 2⁻3. And on right-hand side, I have a corresponding zero divisor graph. Now this element A, B, C are the atoms. Atoms means elements which are just above 0. Now A mid B is 0, that's why A and B are adjacent here. B and C are 0, that's why B and C are adjacent. And A and C are adjacent because their mid is 0. Likewise, we have a zero divisor graph. Now, if you look at the zero divisor graph, since we have K3 here, so naturally 3 colors are enough to color this graph. And one can see that number of atoms are also 3 here. So coloring has, if the poset is atomic, that means atoms are there, elements which are just above 0, then the number of colors to color the graph is nothing but the cardinality of set of atoms. So this is a very nice connection we have. Here is this graph and coloring. And this was the result by Halas and June, Lu and Wu and myself, which says that if we have a zero divisor graph with click number finite, then the graph is weakly perfect. That is the first thing. And you need how many colors? You need the cardinality of minimal prime semi-ideals. So that's a connection. And moreover, if the poset is atomic, then this click number and chromatic numbers are equal to number of atoms in that poset P. So that's a good connection. So I will make use of this fact, that is the number of atoms of that poset. So in today's talk, the perfectness and chordalness of zero divisor graph is characterized in terms of atoms of that poset. So atoms will play a very crucial role afterwards. And what we are planning to do here is, instead of considering whole poset, why not compress that poset? So to compress that poset, let me give an analog of annihilator of ideal. So if I consider A perp, which is a set of those X in P such that XAL is 0. So in ring theory, what we have is, this is essentially the annihilator of X, annihilator of A. So sort of, I'm just giving you analog how we are proceeding. In ring, we have this annihilator of A to be an ideal, but in posets, we have A perp, which is a semi-ideal. Now what I'm going to do, let me give an equivalence relation. So we will say that A and B are related if their annihilators are same. So if the poset is pseudo-complemented, A star equal to B star, this is a very famous congruence relation in case of pseudo-complemented poset. So similar type of thing is also here. A and B are related if annihilators are same. And then what you can do, you collect all equivalence classes, and let us denote it by P tilde square P tilde. That is a collection of all equivalence classes. Now what I can do, I will define a partial order on these equivalence classes. You define equivalence class of A is less equal to equivalence class of B if and only if B perp is contained in A perp. Okay. So now from poset, we have compressed, this poset we called as a compressed poset. Afterwards, I will use the word compressed poset. So we have a compressed poset where the elements are clubbed together whenever their annihilators or perps are same. Now, this is one partition we will get. One poset we are getting. Another thing is there is a partition given by Afkami. If you have a poset with n atoms, everything we are playing with atoms. Let us denote P I1, I2, Ik is a set of those X in P such that X is above Q1, Q2, Q3, Qk, but not above rest of the atoms. Okay, so if I mean P1, that means this will be a set of those elements X which are just above first atom, but not above rest of the atoms. Okay, P2 will be a set of those X which are above second atom. First of all, you have to label the atoms and look at that thing. So this is one more partition, and one can see that this will again partition the poset P. Of course, when I'm saying partitioning, that is P minus 0 here. 0 is excluded. Now, if I define another relation, double tilde, and we will say that X is related to Y if and only both are in the same partition. So one can observe that these two relations are same on P minus 0. So we have two partitions and we have corresponding posets. So what we are doing here, so these PIKs we can club together and we will have a poset. Now let us consider another poset is coming from double tilde relation. So this is PI1, PI2, IK, where I1, I2, IK is subset of 1 to n and they are non-empty. Then you can see that this is a collection of all equivalence classes which are on the set P minus 0. So 0 is not included. So what we are doing here, I'm attaching P0 that will work as 0 of this poset. So I have two poset. One is coming from relation tilde. One is coming from relation double tilde. In tilde, we have A perp equal to B perp. And in double tilde, it is related to elements which are above the atoms. And as I told you, these two relations are same. So these posets onwards, we will simply denote it by square P. These two posets are they are one and the same. So we will denote it by square p. So that I'm calling as my compressed poset. So naturally, whatever, suppose I have N5, very famous example from lattice theory. So this is P, then square P will look like this. This is my square P, because the elements, suppose if I call this is A and B, their perb is same, so they will compress, and what I'm getting is square P. So this is my square P poset, that is compressed poset. Now let me give you a few more details about the zero distributive poset. Zero distributive poset is a generalization of zero distributive lattices. And what it says, if we have Q1, Q2, Qn, these are the atoms, then if I take Qi here and Qi, you can see that Qi is dropped here, their U, that is the upper cone, and take it slower, it is going to be 0. This gives me that this partition is always non-empty. Because of this observation, what we have is the partition P1 to I-1, drop ith thing, I plus 1 to n. This will give me non-empty partition. But keep in mind that in general, this is the we are dropping one entry, ith entry, and we are getting non-empty. But in general, for zero distributive poset, this won't be true. Here is one example. Here Pij, if I consider I and j are from set 1, 2, 3, 4, that means let us look at P12. P12 will be empty here. P12 will be empty. So, but if I consider P123, 100% it is non-empty. So since we are playing with 4 atoms here, so P123, you take any 3 indices here, distinct indices, then that partition is always non-empty when we have 4 atoms. Okay, with this preparation, there was one result which says that was by Monjardet and Monjardet, which is that if the atoms have pseudo-complements, then poset is pseudo-complemented. And if I look at the square L or square P, that is going to be the section semi-complemented poset, that is worked with my student Nilesh Munlik. So if I have a zero distributive bounded lattice with finitely many atoms, so here we are dropping the finiteness on the whole lattice. What we are considering, we are using finiteness of atoms only. Then the square L, the compressed poset, becomes Boolean lattice. And this is the very crucial part which I'm going to use afterwards. Let me give you the 2 main results which I'm going to discuss with you. That is, one is chordal and one is perfect. The concept of chordal graph is very well known. So, and n of v is the neighborhood of v. So these are some standard notations. Again, as I told you, in case of posets, we consider square p, that is the compressed one. So why not use a similar technique while discussing the chordalness and perfectness of graphs also. Again, on graphs, we consider one more equivalence relation. U is equivalent to V if U is same as V, or if this is an edge, then neighborhood of U minus V should be same as neighborhood of V minus U. And this will be an again equivalence relation. So again, you collect all equivalence classes, and this you define an edge in these equivalence classes. U is adjacent to V if and only if U is adjacent to V in graph G, whenever the equivalence classes are distinct. So this will give you a new graph structure. And there is very nice relation between this graph, that is the compressed or reduced graph, what we called as G reduced, onwards we will write it as G reduced, and the compressed poset. What it says that if we have a GP as the zero-divisor graph and GCP as the complement of zero-divisor graph, then if I consider the complement of zero-divisor graph and take its reduced graph, consider the complement of zero-divisor graph and reduced it by using previous relation. It is similar, essentially same as the complement of zero-divisor graph of compressed poset. And this will help me to work with lesser vertices. That is the first foremost application of this result. And the interesting thing is that if G is chordal, if and only if G reduced is chordal. This is another benefit I'm getting. Using few more results, we have the first characterization. If P is a finite poset such that square P, that is the compressed poset, is Boolean lattice, then the zero-divisor graph is chordal if and only if either P has exactly one atom or P has exactly two atoms with the Pi, the partition what we are talking about is the cardinality is 1. One of them has cardinality 1. And if P has 3 atoms, exactly 3 atoms, then the cardinality of Pi has to be 1 for all I. This is the case with zero-divisor graph. What happens to the complement of the zero-divisor graph? We have very nice characterization. It says that the complement of zero-divisor graph is chordal if and only if P has at most 3 atoms. So the whole characterization deals with the atoms only, number of atoms. And just I will request you to remember this fact, because afterwards when we will go for application, we will need these results, okay? This is the whole thing about the chordalness. Now, here I'm asking that P should be a square P should be a Boolean lattice. As we have already observed that if L is zero distributive lattice with finitely many atoms, then square L is Boolean lattice. Okay. So if I consider, instead of considering general zero distributive lattice, if I consider finite zero distributive lattice, naturally it will have finitely many atoms and therefore square L is Boolean. And therefore what I'm getting here is, as a consequence, if L is a finite zero distributive lattice, then naturally we will have these conditions. Why I'm stressing this fact that because in most of the cases when we deal with the graphs associated with algebraic structure, we are able to construct a poset, because the basic idea here is that given a, suppose for example, if I'm looking at the comaximal ideal graph, so what I'm going to do there is from ring R, I will try to construct a poset. And in most of the cases, we are able to construct a zero distributive poset or a zero distributive lattice. And we can, once we have zero distributive lattice or zero distributive poset, things becomes much more easy. So I will make use of this fact afterwards. So this is one more characterization. And instead of considering zero distributive lattice, let us concentrate on a very particular case, direct product of posets with ZPI, that is the zero-divisor graph of Pi is 0. That means these are the posets with single atom. Or I can say that this will replicate the idea of direct product of chains. So it says that in that case, suppose P is the direct product of chains, then GP is chordal if and only if the number of chains is 1. If 2, then each chain has to be C2, some chain has to be C2. And if number of posets are 3, then each chain must be of length 2 only. Okay, and GCP is chordal if and only if number of atoms are less equal 3. So these are the, in some sense, what you can say is a role model for replicating zero-divisor graphs of reduced rings. So I will make use of this result for the application of zero-divisor graphs of reduced rings. Okay, this is the whole story about the chordalness. Let me concentrate on another aspect, that is the perfectness of zero-divisor graphs. So strong perfect graph theorem is a very well-known result which talks about the characterization of perfect graphs. I am using this result to prove the characterization. Okay. And we also know that the chordal graphs are perfect. Okay. Again, the compressed or reduced graph, which we consider, is again useful. There was one more relation which was given by Bagheri on the graph, which says that U is equivalent to V if neighborhoods are same. Okay, and again you define a graph square G. So U and V are adjacent, that equivalence classes are adjacent if U is adjacent to V and the classes are distinct. Again, there is a nice relation. So if you take the zero divisor graph of poset P, apply the previous relation, that is the equivalence relation given by Bagheri. Whatever graph we are getting, that is again a compressed graph, that is essentially the zero divisor graph of this compressed poset. So they are interlinked. And this was the result which is known due to Bagheri, which says that G is perfect if and only if square G is perfect, that is compressed graph is perfect. With this, we have the next characterization for zero divisor graphs of posets. What it says, if P is a finite poset such that square P, that is a compressed poset, is Boolean, then GP is perfect if and only if P has at most 4 atoms. So again, perfectness deals with the number of atoms we have. And if I combine few more results, it says that the zero divisor graph is perfect if and only if zero divisor graph of a compressed poset is perfect. If and only if you have at most 4 atoms, GP does not contain an induced 5 cycle, or G square P, that is a compressed zero divisor graph, does not contain an induced 5 cycle. And in fact, last says that P does not contain a mid subsimilarities isomorphic to the following figure. So if this structure comes in a lattice or a poset, then naturally the zero divisor graph of this poset won't be a perfect zero divisor graph. And I will make use of this result to prove that the comaximal graphs, comaximal ideal graphs of rings are perfect. So in that case, what I'm planning to do here is, if we have, this is my, suppose ID R be the set of all ideals of a ring R, and take a dual of this ideal. So naturally what is going to happen, this will be the zero of ID R star. This is my, let us call, this is my dual of ID R. The zero will be R, and suppose I have a maximal ideal M1, let us call M2, let us call M3, this is my M4, and this is my M5. So these are the maximal ideals. So if I consider the dual of the ideal lattice, the maximal ideals are nothing but the atoms. And naturally one can see that the ideal lattice of a ring R is always one distributive. And therefore, if I take a dual, it will be a zero distributive. So naturally, what will be the join? Join will be the intersection here now. This will be M1 intersection M2 and so on. And you can prove that if I have more than 4 maximal ideal, this structure is going to be there in ID R star. That is the dual of IDR. And naturally, it won't be a perfect graph. So I will make use of this fact afterwards again. Okay, as I told you again, zero distributive lattice has very nice connections. So it says that the zero divisor graph of zero distributive lattice is perfect if and only if click number is at most 4. And same story, we can repeat for direct product of chains also. With this preparation, let me come to the application part. Now, as I told you, there are many graphs associated with algebraic structures. So the first graph which I'm considering is the comaximal ideal graph, that is CGR. So here the vertices are the proper ideals of R that are not contained in the Jacobson radical, because if you look at the adjacency, adjacency is that I and J are adjacent if I plus J is whole ring R. And if I take any two ideals which are sitting inside Jacobson radical, they won't be adjacent. So that will form an independent set. So that's why they are thrown out. So we are considering proper ideals which are not sitting inside the Jacobson radical. So adjacency is I plus j is whole ring R. That means I and j are comaximal ideal. What we consider, instead of considering proper ideals which are not in Jacobson radical, let us put a star here. I'm considering all non-zero proper ideals, may be sitting inside Jacobson radical or may not be sitting. We are not bothering, and let us put a star here. So what we are getting here is that CGR star is nothing but CGR, that is the disjoint union with independent set M. So what is this M? M is nothing but the cardinality of Jacobson radical -1, because 0 is thrown out. So that will be the cardinality. So this is the relation with modified comaximal graph. Why I'm considering so? Because ultimately I'm playing with the IDR star, that is the dual of the ideal lattice. Okay, so these are very, what you can say, standard definitions of modular lattice and one distributive lattice. And as I told you, if R is a commutative ring with unity, then IDR is a modular lattice and it is one distributive. So if I consider dual of it, naturally the dual of modular is modular and dual of one distributive will be zero distributive. So using this thing, what we have is the following main result. If I consider R to be a commutative ring with unity and L star be the dual of IDR, that is, which is going to be the zero distributive lattice, then the comaximal ideal graph of a ring R is essentially the zero-divisor graph of IDR star. That means comaximal graphs of ring you can study via zero-divisor graphs of zero distributive lattices. So this is one important observation. Now what I can do, since the lattice is GL star, this L star is zero distributive, and I can apply all the previous results which we have proved for perfectness and chordalness, okay, to this comaximal graph. And we have the characterization. If R to be a finite Artinian ring with finitely many ideals, then CGR, the comaximal graph, is chordal if and only if, as I told you, we are considering IDR star. The maximal ideals are nothing but the atoms of IDR star. Okay, so this will be the R. These are the maximal ideals. So M1, M2, M3, something like that. So maximal ideals are nothing but the atoms. So naturally, if you recall the previous results, so we have poset has only one atom. That means we have only one maximal ideal. So that means that ring has to be a local ring. Okay. If we have two maximal ideal, and what we are saying is that PI has to be cardinality of PI is 1. That means there is nothing above that. That means it has to be a field. One Ri has to be a field. And if it is a direct product of fields F1, F2, F3, if R is a direct product of Ris, then Ris has to be fields, and the cardinality of this I goes to 1 to n, that n will be 1, 2, 3 only, at most 3. And if I look at complement of CGR, that is comaximal ideal graph, then this will be chordal if and only if we have at most 3 maximal ideals. And similarly, I can go for perfectness also. CGR is perfect if and only if the max R is less equal to 4. And in fact, there was one result which talks about the one way. That means if the cardinality, here is a mistake. So it should be cardinality of max R. Cardinality of max R. If this is less equal 4, then CGR is perfect. So by using our result, we getting the characterization. So here is a one-way implication. Now let me go to the another graph. Again, this is associated with ideal graph. We call it as a co-annihilating graph, which is due to Akbari and others. Again, vertex set is set of non-zero proper ideals, and two distinct vertices I and j are adjacent if annihilator of I intersection annihilator of j is 0. And there was another definition. This was co-annihilating. We called it as a CAG. So this CAG stands for co-annihilating graph. Let us have annihilating graph. So AGR. So again, here Vishweswaran gave a definition of annihilating ideal graph, where the vertex set is set of all non-zero annihilating ideals they are considering, and I and j are adjacent if I plus j is an annihilating ideal. So instead of considering annihilating ideals, we modified again the vertex set. Instead of considering all non-zero annihilating ideal, why not consider all non-zero proper ideals? That is the change. And again, here we put a star. So that condition is removed. And again, adjacency will remain same. That means I and j are adjacent if I plus j is annihilating ideal. In case of Artinian ring, we have a very good connection. What it says that if I and j are adjacent in co-annihilating ideal graph, I and j are adjacent in co-annihilating ideal graph, we are getting that I plus j is R. That means I and j are comaximal ideal. So that is a good connection in case of Artinian rings. And because of that, this is a result due to Akbari, which says that comaximal ideal graph is essentially same as co-annihilating ideal graph whenever a ring is an Artinian ring. So using this fact and previously observed remarks, we have comaximal ideal graph that is modified, which is equal to comaximal ideal graph with independent set, disjoint union of independent set with M. What is M? M is nothing but the cardinality of Jacobson radical minus 1, which is same as co-annihilating ideal graph, co-annihilating graph. And this is complement of annihilating graph that is modified. Whenever I put a star, that condition is removed, and this is annihilating ideal graph. The complement of annihilating ideal graph, they remain same. And again, apply previously known result, because ultimately it has to play with the comaximal graph, comaximal ideal graph essentially. And comaximal ideal graph, we have already studied that can be studied via zero-divisor graphs of zero distributive. And applying previous results, we are getting the same thing, the characterization for chordalness and characterization of perfectness. So these two things we can combine for annihilating, co-annihilating, co-maximal graphs. So these three graphs can be handled in a very efficient way via zero-divisor graphs. Now let me go to the one more graph. This was work with John Lagrange, myself, my student Sarika Devare and John Lagrange. What we observed is the previously John Lagrange and Roy observed that if we have a reduced string, reduced Artinian ring, exactly K prime ideas, then we can write that R to be a direct product of fields. And we observe that here the zero-divisor graph is nothing but the zero-divisor graph of a reduced string R, okay, is nothing but the zero-divisor graph of direct product of fields. And what we consider there, I'm not giving you much detail. That result was later considered for semi-groups also. On a reduced semi-group, we define a partial order and consider the corresponding poset. So R is with me, which is a reduced string. So define a partial order on R and construct a poset. And you will observe that the zero-divisor graph of a reduced string in terms of ring theoretic aspect, that the graph which I'm considering is a zero-divisor graph in terms of ring theoretic aspect, is essentially same as the zero-divisor graph of the corresponding poset which we derived from the ring R. And because of that, you can observe here, this is the, on left hand side, you have the zero-divisor graph of a ring. This is ring theoretic graph, okay, and this is poset theoretic. So again, the zero-divisor graphs of reduced string can be handled via zero-divisor graphs of posets. That is one observation. In fact, there is a very nice connection with a number of minimal prime ideals of a ring R when R is a reduced string. With my co-author Ganesh Kadu, we could establish the relation. If we have a reduced string and you have, suppose, n minimal prime ideals in that ring R, then construct a poset out of that ring R. That poset will have n minimal prime semi-ideals. So that is a bijection. And via poset theoretic way also, we can get the result of Bake also. Okay, so using again same technique, we can talk about the chordalness and perfectness of zero-divisor graphs of finite reduced string. So these are the two more results what we have. Now let me go to the another part. If I consider the poset P, script P or bold P, you can say, it's a direct product of posets which has exactly one atom and exactly one dual atom. Then the zero-divisor graph of P and its dual both are equal. And in that case, if I consider the direct product of chains, then in that case, the zero-divisor graph is equal to the zero-divisor graph of C dual. That is the important observation which we will use. Now, let me talk about another application, that is the intersection graphs of ideals of Artinian principal ideal ring. Now, intersection graphs are well studied, and particularly Chakrabarty and others consider the intersection graphs of ideals of rings whose vertex set is the non-zero proper ideals, and two distinct vertices I and J are adjacent if their intersection is non-zero. That means non-trivial intersection, then they are adjacent. Then what we observed is the following. The intersection graph of ring R is nothing but the modified zero-divisor graph of IDR and take its complement. And IDR is again a lattice. So that means in some sense, we are talking about the modified zero-divisor graph complement of a poset. So intersection graphs can be handled this way. And if I consider the special ideal rings, SPIR, then we know that if we have a maximal ideal M, then there exists N such that M to the power N is 0 and M to the power N minus 1 is non-zero. And every ideal I, you can write some power of M. So in this case, M is a nilpotent with index of nilpotency is equal to N. Then again, lattice of ideals of R is essentially isomorphic to the chain C of length N plus 1. So that's why, again, we consider the special principal ideal ring. And this will give me that this R is isomorphic to direct product of Ri's. Then this will have a prototype of direct product of chains with Ci. And if the maximal ideal Mi has nilpotency index Ni, then the chains are of length ni plus 1. Chains are of length ni plus 1. So again, I can apply the previous results for chordal and perfect. We have these things. And lastly, I will talk about the intersection graphs of Zn, because main idea was why to consider principal ideal ring. So prototype was Zn. So this result was known for intersection graphs of Zn are perfect if and only if this n is direct product of 4 distinct primes. Okay, at most 4 distinct primes. So that was the result which was known. So that can be handled via previous results. So these are few references which talks about the perfectness and planar co-annihilating ideal graphs. Here is a paper where the Beck's conjecture, the counterexample for Beck's conjecture is given. And here is a paper where the definition was modified and it is proved, many important results are proved here. Here is comaximal ideal graph. This is the main paper where the theory started, that is the Beck's paper, coloring of commutative rings. And in this paper, the intersection graphs are studied very well. In this paper, first of all, we have characterized the zero-divisor graphs, which are perfect zero-divisor graphs. And in case of non-commutative rings also, our method worked here. That is worked with Avinash Patil and B.N. Mafari. This result is generalized in the paper. Thank you. I'm done.
Thank you very much. Let's thank the speaker. And that was a very nice talk. Thank you. I'll turn off the recording now and we'll take questions.